Continuing on page 11, we have our first, let's plug these numbers in and check out our process to figure out specific amounts of electrostatic force. And we're going to definitely use our guide, the jot down all known, determine the quantity you're solving for, arrange a matching formula for what you're given, do the math, evaluate. So we have here, given the charge on a single electron is approximately 1 6/10 times 10 to the negative 19th coulombs. Remember, coulomb is how much charge, okay? The SI unit of charge is the coulomb. And the K is equal to 9 times 10 to the 9th Newton meters squared per coulomb squared. What would be the repulsive force between the two electrons? All right, so this question is asking how much are these electrons pushing away from each other? How much force are they repelling from each other? Using the guide strategy and guide method, it's located on page 0 of the study guides. First thing you do is jot down all the information that is given for yourself. So we have given the charge on a single electron is approximately 1 6/10 times 10 to the minus 19 coulombs, and that represents the amount of charge. Q is the symbol for charge. Coulomb is the SI unit of charge. The symbol, the unit. We are also given the K value, 9 times 10 to the 9 Newton meters squared per coulomb squared, and that is the K value. What would be the repulsive force between the two electrons? So what we're looking for is a repulsive force. We're looking for the electrostatic force. Now we have the unknown and the givens. We go to the letter I. We identify. We arrange a matching formula for what you're given. Well, let's see here. Shockingly, the day's been about Coulomb and Coulomb's law. I'm thinking the equation begging to be used is Coulomb's law. Electrostatic force directly proportional to the proportionality constant. Q1, Q2, distance squared. So we have the K value. We have Q1. Oh, we don't have Q2. We don't have Q2. We don't have Q2. Let's see here. Given the charge on a single electron, repulsive force between the two electrons, two electrons. So we really have this twice. This is Q1 and this is Q2. All right, and distance. Oh, we don't have the distance. We do have the distance. Always look at the pictures. Right here's the distance. 6 times 10 to the negative 11 meters. So we are given the distance. That's part of our knowns as well. That 6 times 10 to the negative 11 meters is the distance. So if I were to take and plug this in now, all right, something that I do, not really sure why, started in college, and I guess it just lasted, is I always write down the K value, but I don't plug in the quantitative, the number portion until the very end. One of the reasons I do this is it helps me to find my errors a little faster if I wait to plug in the K value. So I write down the letter K. Q1 is 1.6 times 10 to the negative 19 coulombs. That's 1. Now I have to do another coulomb, or excuse me, another charge. That is 1.6 times 10 to the negative 19 coulombs. This is all divided by the distance squared, and the distance is 6 times 10 to the negative 11 meters, and that is squared. All right, my electrostatic force is equal to the K. Now what I'm going to do is square the charges. Now, we've been saying square the distance, but we square the charges because the charges are the same value. This is Q1 times Q2, so it's really Q squared. All right, 1 6/10 times 1 6/10. 1.6, 1.6. 6 times 6 is 36. Carry the 3. 6 times 1 is 6. Plus 3 is 9. 0 because I'm moving over a place value in my multiplication. And 1 times the 16. So 16. Then I add the partner with multiplication. We have 6 plus 0 is 6. 9 plus 6 is 15. Carry the 1. 1 plus 1, 2. And I have 2 decimal places, so I'll put that there. So 2.56 times 10 to the, all right, I have negative 19 and negative 19 as my exponents. When you multiply exponents, you add them. This was part of the review in the earlier pages of your study guide with the scientific notation. Negative 19 plus negative 19 is minus 38. Coulomb times Coulomb is Coulombs squared. Coulombs squared. Now you can definitely use a calculator. One of the things that I want you to recognize through doing this is that you can do scientific notation on the 4-digit calculator in the sense of we just multiply, we add, and we divide these values. All right. Now let's go ahead and square the distance here. All right, 6 times 6 is 36 times 10 to the negative 11 squared, meaning negative 11 times another 10 to the negative 11th, is really adding negative 11 plus negative 11. So that is negative 22. And that is also squared for the units, meters squared. Now let's divide, or change the slide. Let's divide these two quantities. So I'll bring down electrostatic force is equal to, and I just leave the K value as the last number that I'll bring into the solving of the equation. So now what I need to do is take 36 into 2.56. All right, 36 will not go wholly into 2, so 0, decimal. 36 doesn't go wholly into the 25, so I put a 0. 36 will go into 256, and that is about 7 times. Give it a whirl. 7 times 6, 42. 7 times 3, 21 plus 4, 25. And we're dividing, so our companion is subtraction. 256 minus 252 is 4. And 0, bring that 0 here. 36 will go in 40 one time. And the reason I was doing this 1 was to see if this would remain a 7. If this number had turned out to be greater than 5 or greater, then I'd have recorded decimal 08. So this 256 2 and 56 hundredths divided by this 36 turns out to be 0.07 times. Now I'm going to divide these exponents. Remember, the companion to division is subtraction. Reviewing from earlier pages, scientific notation, when we have these two exponents, you do subtract them. You take the top minus the bottom. So minus 38 minus negative 22. Remember, minus in math is plus the opposite. So negative 38 plus a 22 is going to be times 10 to the, subtract the 22, so you'll get to the 16. 16 and 22 is 18. Check myself, 38, yes. and it's negative because the 38 is larger than the 22. Now, little heads up for you. If you took this top value and divided by this bottom value in your calculator, you're probably getting your calculator to not have this to the 16th power. You'll see it's because I did my division by hand over here rather than the calculator, and this isn't currently correct scientific notation. Scientific notation is one whole number. And likewise here, I did 36 times 10 to the negative 22nd. So this isn't improper scientific notation. And the reason I'm not putting it in proper scientific notation is I want to show my friends that you can use a 4-function calculator. You don't have to have the fancy calculators with the exponents. So, but many of you in the classroom do have those calculators that will do the exponents. Please note this is why my step right here probably looks different than your calculator output. My units with the division, I have this c squared, Coulomb squared, divided by meters squared. What we have left to do then, let's make this a little clearer for ourselves here. Just distinguish the next step for ourselves. What we have left to do is take this number and multiply by the k value. So my electrostatic force will be the k value. Now I'm actually write what the value is. 9 times 10 to the 9th Newton meters squared per Coulomb squared, multiply by this, times 0.07 times 10 to the minus 16. This is a big old scribble. Here's minus 16. Coulomb squared per meters squared. So multiplication, 9 times this 0.07. Well, 9 times 7 is 63. Now I have this 2 decimal places, so 2 decimal places, times, I have 10 to the 9th and 10 to the negative 16. 9 plus negative 16, because I'm multiplying exponents, you actually add them. 9 plus negative 16, 10 to the negative 7. The units, if we see here, I have a Newton meter squared per Coulomb squared, and that's being multiplied by a Coulomb squared per meter squared. Again, let's just add a color here to make this stand out a little bit for you. This meter squared will cancel. This Coulomb squared in the numerator cancels this Coulomb squared in the denominator, and you're left with the units of Newton. Hey, what is supposed to be the SI unit of force? Indeed, the Newton. This is one of the reasons why I like to keep my units all the way throughout the problem. By doing that, if I'm working through the math of the units and I see my unit ends up with what it's supposed to be, I'm pretty confident that this number is correct. Ooh, is this number correct? Now my number here isn't fully in scientific notation. As scientific notation, you have to have a whole number, 1 through 9. So I have this less than the number 1, so I need to move this decimal to here. So in proper scientific notation, 6.3 times 10 to the negative, it's either going to be to the negative 8 or to the negative 6. Well, the way you can check yourself is to actually take it out of scientific notation. So I have decimal 6.3 times 10 to the negative 7. If I take it out of scientific notation, the negative go to the left. So I have decimal 6.3 go to the left 7 places. 1, 2, 3, 4, 5, 6, 7. As you know, I like to put the leading zeros. I fill in the zeros here, And now I want to know, okay, is this number right here, to put in scientific notation properly, to the -8 or to the -6? So let's do that. We want 6.3. So this is the number we want to now put back into scientific notation correctly. Just change the color real quickly here, make it stand out a little bit, maybe. So I'm going to go 1 and wipe out the whole thing. 1, 2, 3, 4, 5, 6, 7, 8. 6.3 times 10 to the -8. And you can always check that again if you wanted to. Take that 6.3, move it 8 places. 1, 2, 3, 4, 5, 6, 7, 8. Do you have 1, 2, 3, 4, 5, 6, 7? 1, 2, 3, 4, 5, 6, 7. All right. So the answer is, in proper scientific notation, 6.3 times 10 to the -8. Don't forget our units of Newton. Newton. Now, sit back and catch your breath for a moment. That problem of your first Coulomb's law calculation, it definitely took longer than problems we've done in the past. Say, oh, volume is length times width times height. Volume is 4 meters times 4 meters times 4 meters, and we're done in a snap. 4 times 4 is 16, and 16 times 4 being 64. We're doing the same thing with Coulomb's law as we were in the past with these, what we might say, faster working equations. We just have to recognize that it's taking us more time, just because we have some more steps. These Coulomb's problems, they're not harder. You're still doing basic division, multiplication. Okay, you're doing the same basic calculations, but sometimes as you approach Coulomb's law, whether you're 9, 10, 11, 12th grader, you look at this and sometimes get overwhelmed with, oh, this is so much harder because it's taking me so much more time. It's not harder. It is taking a little bit more time, but it's not more time because it's harder. It's more time because there's more steps than we've had to do before. You're squaring values on the top. You're squaring values on the bottom. You're adding this k value. Well, I shouldn't say adding. You're including this k value and multiplying the k value. So there are more steps. They're not harder steps. They just take more time. Turn to your lab buddy and tell them, Coulomb's law problems, they're not harder than what we've done. They just take a little more time. Not harder, just take a little bit more time. We have a force of 2 4/10 times 10 squared newtons. Newton, the SI unit of force. And this is the amount of force that is between a positive charge, 8 times 10 to the -5 coulombs, and a positive charge of 3 times 10 to the -5 coulombs. What distance separates the charges? Well, first of all, turn to your neighbor and ask, is this an attractive force, or is this an amount of repulsive force? We have a positive charge, and another part is positive charge. So we're going to be calculating the distance between this amount of force these two charges are exerting through repelling one another. So we're going to figure out how far away are these charges from one another. The first step of our guide steps, of course, will be to jot down the numbers. So go ahead and jot down those numbers. We have 2 4/10 times 10 squared. Made this a little bit more accurate than in the problem. 2 4/10 times 10 squared newtons. So that is a force, and this is electrostatic force. Between a positive charge of 8 times 10 to the negative 5 coulombs. Coulomb is the amount of charge, the SI unit of charge, and the symbol for charge is Q. Positive charge. So this happens to be a proton. And then we have another positive charge, another proton, so Q1, Q2. And this one right here is 3 decimal times 10 to the negative 5. So we don't actually have 2 protons. As you remember, every proton is identical in mass, amount of charge, sign of the charge as every other proton. So this is actually a positive amount of charge, a second amount of positive charge, not 2 same protons because the values aren't the same. And we're trying to find distance. Trying to find the distance. All right, so we're going to use Coulomb's law. Not a surprise there, I'm sure. Continued. Coulomb's law is the K value. Oh, they didn't give us a K value in the problem. That's okay. It will always be on your reference sheet. You will always have the K value is 9 times 10 to the 9th Newton meters squared per Coulomb squared. K value directly proportional to the 2 charges, inversely proportional to the distance squared. Now you could certainly go ahead and plug in the numbers into this equation, but notice that your I identify step. You need to arrange a matching formula for what you're given. We have a formula for what's been given, but we want to match it for what we're trying to find. And we're trying to find the distance. Now, notice distance, electric force. Tell your neighbor how they're related. Directly, constantly, inversely, inversely. So to rewrite this to match in terms of solving for the distance squared, we know that force and distance squared are inversely related. So I can just flip those two. And my numerator will stay the same. Now it's about plugging in the values. So you do the math. Guide step of D, do the math. Substitute your numbers and units for these variables. So the distance squared, string here to give us some more room, the distance squared is equal to, and this is just an oddball thing I do, that I do the substituting of the value of K in last. My Q1, and it doesn't matter which one you call Q1 or Q2, we have 8 times 10 to the negative 5th coulombs. I'm going to multiply that by 3 times 10 to the minus 5 coulombs. And I divide all of that by electrical force, which is this first number that was given to us. 2 4/10 times 10 squared newtons. Now I can go through, multiply these two values. Distance squared equals the K value, 8 times 3, 24, maybe, times 10 to the negative 5th, well, I add those, I'm multiplying the exponents, I add them, minus 10, a coulomb times a coulomb is a coulomb squared. Then we divide by 2.4 times 10 squared newtons. Extend this out, my K value. Now we're going to divide. Well, 24 divided by 2 4/10 very nicely works out to be 10. 10 times 10 to the, I'm going to subtract these. It's going to be minus 10 minus 2. Minus meaning plus the opposite. So 10 times 10 to the negative 12. And the units are going to be Coulomb squared divided by a Newton. So here's the next thing I need to do, is I need to multiply the K value by what I just divided. Distance squared equals the K value, 9 times 10 to the 9th Newton meters squared per Coulomb squared. And that will be multiplied by this 10 times 10 to the negative 12 Coulomb squared per Newton. So I've just copied this down here and replaced the value for K. That's what this step here. And just continuing on, 9 times 10 is 90 times 10 to the 9 plus negative 12 will be negative 3. And my units, well, Coulomb squared here and the bottom cancels the new Coulomb squared up top. My Newton at the top cancels with the Newton at the bottom, and I'm left with meters squared. I'm left with meters squared because this is distance squared. So tell your labby, what's this final step then? Yes, I need to find the square root. My distance squared, well, let's take it out of scientific notation so that we can find the square root through our handy calculators. Minus 3, so I take this 90, move the decimal 1, 2, 3 to the left. Make sure that's right. 1, 2, 3 to the left. 1, 2, 1, 2, 3. So decimal 0, 9 meters squared. So distance squared is 0 decimal 0, 9. 1, 2, 3. Yeah, just making sure. Meters squared. And I'm going to find the square root. Square root. And so my distance now will equal the square root. So decimal 0, 9, just using a calculator here to find the square root, turns out to be 3/10. Square root of the meter squared is a meter. We can check ourselves here as decimal 3 times itself, squaring. 3 times 3 is 9. We have these two decimal places, so 1, 2. Yep, the square root of decimal 0, 9, 900ths is 3/10. Oh, 3/10 squared, 900ths. So the distance is 3/10 of a meter. 3/10 of a meter. Let's take a moment and look at page 10. Let's look at this page and congratulate yourselves on the work that you've done. You have begun page 10 by thinking conceptually about the idea of Coulomb's law, how the electrostatic force directly related to the product of two charges, and how electrostatic force is inversely related to the distance squared of those charges. And you've done a couple of calculations on page 10, and many more thoughts and calculations done on page 11. So you need to step back and realize just what amazing things that you have done with Coulomb's law. Congratulations. For the next 5-minute increment or thereabouts, we are going to put you in the hands of Paul Hewitt, really famous among physics teachers, famous physics teacher himself. And Paul Hewitt, in fact, got his master's of physics in Cache Valley at Utah State University, home of the Aggies. And I've had the opportunity to actually work with Mr. Hewitt on a few projects in the past. A friend of mine taking this photograph, Paul getting a little sick of the flashes of camera, so giving the profile thumbs up shot. So sometimes it helps to hear Coulomb's law presented to you through a different voice. So here is Paul Hewitt with his Hewitt Drew It.
Imagine a universal force like gravity that varies inversely with the square of the distance, but which is billions upon billions times stronger. If there were such a force, and if it were attractive like gravity, the universe with all its matter would be pulled together into a tight ball. Yuck, not good. But suppose this force were a repelling force, where every particle repelled every other particle. What then? The universe would be an ever-expanding gaseous cloud. Again, not good. But let's suppose that the universe were composed of both attractive and repulsive forces. Suppose the root of these forces were particles, say, positives and negatives. Further suppose that the positives repel positives and negatives repel negatives, but attract positives. Like kinds repel and unlike kinds attract. And what if there were equal numbers of each? What would the universe be like? The answer's simple. It would be like the one we're living in, for there is such a force. We call it the electric force. Yum. The electric force between things balances out because of equal numbers of positives and negatives. All things around us attract one another electrically, but repel one another just as much. That's why the enormously strong electric forces between Earth and Moon have been balanced out. This is why the much weaker gravitational force, which only attracts, is the dominant force between these two bodies, and the dominant force in the universe. It's a gravitational force that holds the Moon in orbit. Similarly, it's the electric force that holds electrons in orbit about atomic nuclei. For example, in a hydrogen atom, the proton that makes up the nucleus holds an electron in orbit. Charges with opposite signs attract. The fundamental rule of electricity is that like charges repel one another, unlike charges attract. Protons are positively charged and electrons are negatively charged. The attractive force between protons and electrons holds atoms together. A study of chemistry finds various ways that atoms bond to form molecules. Beneath all these bondings are electric forces, all of them. That's why anybody studying chemistry has to know something about electricity. Getting back to the electric force. As strong as it is, it weakens with distance. Like gravity, electric force is an inverse square force. It decreases inversely as the square of the distance between charges. This was discovered in the 18th century by French scientist Charles Coulomb and is called Coulomb's law. Coulomb's law tells us that for charged objects much smaller than the distance between them, ideally particles with point charges, the electric force varies directly as the product of the charges and inversely as the square of the distance of separation. In this equation, Q sub 1 represents the quantity of charge on one particle, and Q sub 2 the quantity of charge on a second particle, and d the distance between them. This force is along a straight line from one charged particle to the other.